Under normal conditions, an industrial electrical system operates in quiet equilibrium. Power moves predictably from the grid, through the lines, into the facility. But a short circuit breaks that equilibrium instantly. As commercial electricity consumption scales up, facilities require massive supply transformers. To handle the load efficiently, engineers are placing these high-capacity transformers closer to main switch rooms. This physical proximity removes the natural resistance of long cable runs. It drastically increases the prospective fault current, or PFC, that can surge into an installation node during a dead short. If an engineer fails to accurately calculate this maximum destructive energy, the protective hardware will be instantly overwhelmed. The result is catastrophic equipment destruction and severe hazards for anyone standing nearby. To protect these systems, we have to isolate the specific type of threat. An overload is a slow thermal stress caused when downstream equipment draws slightly too much current, causing wires to gradually heat up. This diagram compares the two faults. On the left, an overload takes minutes or hours to trip a breaker as thermal energy accumulates. On the right, a short circuit bypasses normal loads. Current spikes instantly into massive amperage, requiring the breaker to act in milliseconds. Short circuits are violent electrodynamic events. Because the downstream load is bypassed, the only factor limiting the energy is the physical impedance of the wiring, located upstream of the fault. A protective device sized solely to handle the normal demands of the facility is completely blind to the terrifying volume of energy the upstream grid can force it through it. To build an accurate mathematical model of a fault, we have to start at the absolute physical ceiling of the system, the grid's supply transformer. The total energy released during a short circuit is capped by this hardware. The transformer's physical size, measured in kilovolt amperes, dictates the maximum theoretical damage it can inflict. Looking at this standard engineering table, we can see the direct correlation between the physical size of the unit and its short circuit output. If we isolate a common industrial installation, a 500 kVA pad mount transformer, we see it generates a 12.5 megavolt ampere short circuit output. That baseline metric tells us the maximum potential energy available before any downstream wiring is even factored into the equation. With the kVA established, the next critical variable is the transformer's impedance, commonly noted as %Z. Impedance represents internal resistance. A 5% impedance rating means it only takes 5% of the normal primary voltage to circulate the maximum full load current through a shorted secondary winding. We calculate the source fault level in MVA by taking the kVA rating, dividing it by 1000, and multiplying by 100 over the %C. For a 500 kVA unit with 4% impedance, the math yields 12.5 megavolt amperes. To find prospective fault current, divide 12.5 MVA by the square root of 3 times 400 volts. This resolves to 18,000 amps of fault current coiled at the transformer. This logarithmic chart confirms our calculation. Finding the intersection of a 500 kVA transformer and a 4% impedance maps exactly to an 18 kiloamp short circuit current. That 18,000 amp terminal PFC is the absolute worst-case mathematical scenario. Any hardware positioned immediately downstream has to be specifically rated to survive that exact force. As the current travels away from the transformer, the physical resistance of the copper conductors acts as a massive braking system on the fault energy. This is dictated by alternating current Ohm's law, where current equals voltage divided by the total circuit impedance. This graph plots fault current against decreasing circuit impedance at 230 volts. Notice the nonlinear relationship. As impedance drops below 0.1 ohms, current spikes violently upward. At 0.01 ohms, a standard industrial value, the current explodes to 23,000 amps. Total phase impedance is highly variable. It depends on conductor length, the wire's cross-sectional thickness, and the choice of metal. This creates a counterintuitive engineering reality. Shortening a cable run or upgrading to a thicker, highly conductive wire actually increases the localized destructive capability of a short circuit. The transformer is the primary engine of a short circuit, but there is a critical secondary variable often missing from baseline estimates: large industrial inductive loads. heavy electrical machinery inherently carries massive physical inertia. When a short circuit occurs, facility voltage plummets, and these spinning motors instantly become generators, dumping their remaining kinetic energy backward into the fault. To account for this in the system architecture, engineers apply a strict multiplier. Calculate the total running motor load in amps, multiply it by 4, and add it directly to the baseline PFC. To safely specify hardware for a switchboard, you cannot use generalized facility data. You must calculate the exact fault current resting at that specific physical node. This engineering reference displays the formulas for node calculations. We look first at the three-phase short circuit equation on the right. It requires taking the open-circuited secondary voltage, U, divided by the square root of 3, multiplied by the total upstream phase impedance. Running the three-phase calculation isn't optional, it is a strict requirement because a three-phase fault consistently generates the highest maximum electrodynamic stress on the equipment. Compare that to the single-phase equation located on the left side of the page. Single-phase faults rely on a different set of constraints, using line-to-neutral voltage divided by the sum of the total line impedance and total neutral impedance. Knowing precisely which formula to apply dictates whether a local breaker panel safely interrupts a surge or violently detonates under the pressure. Abstract mathematics only matter when applied directly to the physical hardware tasked with stopping the fault. Our entire calculation sequence, the source capacity, the line impedance, and the motor contribution, distills down into a single concrete node PFC value. We then place a protective circuit breaker at that specific node. That breaker carries a specific interrupting capacity, rated in kiloamperes. For the system to be safe, that breaker's capacity rating must physically exceed the node's maximum calculated current. If the interrupting rating is lower than the PFC, the breaker is incapable of clearing the fault without tearing itself apart. But an unavoidable problem arises when the mathematically required breaker rating is too massive, excessively expensive, or physically impossible to install in the facility. In these scenarios, engineers install active fault current limiters, such as precisely rated HRC fuses, placing them upstream to artificially bottleneck the incoming energy. Instead of an entire switchboard exploding, a specialized ceramic fuse violently shatters inside a controlled casing, instantly killing the electrical arc. These limiters successfully cap instantaneous fault currents to a predetermined threshold that the downstream hardware can safely absorb. Overcurrent protection is entirely distinct from normal operation. It is dictated entirely by the physics of upstream copper and grid capacity in the exact millisecond that system impedance suddenly drops to 0.